invited me to speak at this. So as Hannah said, yeah, I'm at ECMWF, which is the European Centre for Medium Range Weather Forecasts, and I work in the Model Uncertainty team alongside Martin Leutbecker and Simon Lang. And this work is done with them and also with Michael Diamantakis, who works on the dynamical core of the forecasting model. So I'm going to talk about model uncertainty schemes in the IFS. And I'm going to start with a bit of background, having tested that I could get through the slides. Now it's not working. Hold on. Okay, so I apologise if some of this is a bit basic for some of you. I wasn't quite sure who the audience were, so there's a little bit of background at the start to get everyone up to speed with what we're talking about when we think about ensemble forecasts. So as I'm sure most of you know, forecasting weather is a chaotic problem. The atmosphere is a chaotic system, and so the problem for us, therefore, is that if we have small errors in our model, then they can grow to have a major impact in the forecast later on. And for forecasting weather, the way that becomes a problem for us is that we can never perfectly measure the current state of the whole atmosphere. And I imagine no matter how much computer power we have, no matter how many observations we have in the future, that will always be a problem for us at some level. So this lends itself to an ensemble forecasting approach. And when I talk about ensemble forecasts, what I mean is that for a single start time and a single forecast period, we have a parallel set of forecasts, each of which have a slightly different set of initial conditions and each of which see a slightly different formulation of the computational model. From this set of forecasts, what we intend to do is to assess the uncertainty in our forecast. And on the right here, I've got a couple of examples that have come from our operational forecasting system. So these are two forecasts for two different dates in June, one in 1994, one 1995, for a location in London, and they're for the air temperature at that location. And so on the vertical axis, we have the temperature in degrees C, and along the bottom are days into the forecast, so from the start time through to day 10. And what are plotted, first of all, if we look at the thick blue line, this is the analysis of the temperature after the event. So having got beyond this 10th day, we can look back and we can use our forecasting model to ingest all of the observations available for that period and get our best estimate of what the air temperature actually did during that period. So this is our best guess of the truth, best estimate of the truth. And then in the thick pale blue line, which I hope you can see in the middle of the cluster, is the control forecast. So this is our unperturbed model, which essentially is our best effort at building a single forecast. And this is what we would have. This would be our forecast if we did not have the ensemble forecasts. And then the red lines around, each single red line represents a single member from the ensemble. So they each represent one of these perturbed forecasts for this particular period. And the reason I've put these two examples here is that although they both forecasts look quite different, I would say both of these represent good ensemble forecasts. And the reason I say that is that if you look at the analysis, our version of the truth, in both cases, the truth lies within the range of the ensemble. And it's not at the centre of the ensemble. It's not always close to the control forecast. In fact, you can see in this upper forecast, there's actually quite a big difference between the control forecast and the analysis. And in the lower forecast, there are big differences throughout the forecast. But in both cases, if you track the analysis, you can see that it lies within the range of the ensemble, sometimes right at the edge, but always within the range of the ensemble. And this is for two distinctly different weather regimes. So in the upper case, we've got a really tight agreement between all of these ensemble members out to even sort of day 4 before there's some divergence. So we learn from the ensemble that there's really stable weather conditions for the first 4 days and not a lot of variation in the ensemble members. That's telling us that there's a lot of certainty in the forecast. We should assume there's a lot of certainty in the forecast. And it's not until later into the forecast that we start to see the ensemble members diverging. And sure enough, 1 or 2 members catch this significant drop in temperature in the later part of the forecast. Meanwhile, for the same date a year earlier, the situation is really quite different. For a start, we're starting with much colder temperatures than were observed a year later. But the divergence in the ensemble starts really early. So from day 2, we're already seeing significant divergence in the ensemble members. The control forecast, along with most of the ensemble members, see the temperature continuing to rise up to sort of out to day 3. And then there's a severe divergence between ensemble members. Some members see this quick, very sharp drop in temperatures, and they indeed do pick out this drop in temperature that's observed later on. While other members continue to see these higher temperatures throughout the period. And so what we take from this ensemble forecast is that there's very large uncertainty in the forecast for this location at sort of beyond day 2, going into day 3. And that's really useful information. If we only had the control forecast in this case, we would end up with a very poor forecast even at day 2, day 3. So this is what we're trying to do with Ensemble Forecast. We're trying to provide users with some estimate of how confident they should be in the forecast. That's a bit of background to Ensemble Forecast in general. At ECMWF, we have a forecasting system called the Integrated Forecasting System, the IFS, from which we build an ensemble, which is termed the ENS or ENS. And our operational forecast for the medium range weather is built with 51 members. So we have 50 perturbed forecasts and our 1 control member, which has no perturbations. Excuse me. Our current operational forecast is run at a resolution of around 18 kilometres out to day 15, and then twice a week those forecasts are extended out to day 46 at a slightly coarser resolution of 36 kilometres. And the computational model sees 137 vertical levels through the depth of the atmosphere to represent what's going on through the atmosphere. It's a coupled model, coupled to an ocean model, a wave model and an ice model. And the perturbations for those 50 perturbed members come from perturbations to the initial conditions, which come via an ensemble of data assimilations combined with some singular vectors, and we use a 5-member ocean data assimilation. And then in addition, we have perturbations that represent model uncertainty. And our current operational scheme is called SPPT. And I'm going to talk about that in a bit of detail in the coming slides, just to give you hopefully some clear understanding of what we're trying to do with these model uncertainty perturbations. But from here on, I'm really trying to focus our attention on this aspect of the forecasting model, this representation of model uncertainty. So just a little bit more background. So what we're really trying to get at here, for this ensemble forecast to be useful to us, we need a reliable ensemble. And what we mean by that is that if we could picture our ensemble as something like this, where each ensemble member provides a forecast in some phase space. So this could be that air temperature at that location in London, day 3, for example, into the forecast. Then we have different estimates for that forecast variable from each ensemble member. And we can construct the ensemble mean, which is going to sit somewhere near the centre of the cluster. After the event, we can go out and take the observation, our best estimate of the truth for that event, and we can work out what we're going to term the error of the ensemble, which is the difference between the ensemble mean and the observation. And we can also calculate the standard deviation of the ensemble, which I've represented here as being something like a sort of characteristic radius of this cluster of points. And if we average over many, many ensemble forecasts in lots of different weather regimes for lots of different regions over the full range of seasons, what we would like to see is that there's good agreement between the standard deviation, so the spread of the ensemble, and the error of the ensemble. And if we have that situation, what we have is a reliable ensemble, and we can use, for any new forecast where we don't yet have this observation, we can use the ensemble mean and the spread of the ensemble to give us an idea of how confident we are in that forecast. The common problem for ensemble forecasts is that we end up with an underdispersive ensemble. We don't have enough spread in the ensemble, so that the cluster of points is too tightly packed. And if we compare over many ensemble forecasts, we have a standard deviation or a spread in the ensemble that is smaller than the error of the ensemble. And if we try to therefore use spread of the ensemble from a new forecast to give us an indication of the certainty of the forecast, will issue overconfident forecasts, which forecasters may learn to recognize that the forecast is overconfident. But ideally, what we want is an ensemble where we don't have to make those sort of mental arithmetic to adjust for an overconfident forecast. So the big question really is how are we going to create the perturbations which build this reliable ensemble? Okay, another schematic. So here's my schematic of what we're doing with the ensemble forecasts. So if we have an ensemble that's got a set of perturbed initial conditions, I'm not talking about how we make those perturbations. I've highlighted that we use essentially an ensemble of data assimilations combined with a few other things for the ECMWF ensemble. But we have this cluster of perturbed initial conditions. If we put those through our forecast model and allow each member to see the same forecast model, we will indeed have a set of perturbed forecasts at a later lead time. But what we're asking here is what can we do to represent the uncertainty that comes from this black box that is the forecast model? We know that there must be errors associated with the computations in the forecast model, so can we introduce some perturbations that somehow represent some of that uncertainty? And so essentially what we're talking about therefore is that each ensemble member not only has its own initial state, initial conditions, they now each see their own forecast model. So each member is seeing a different realization of the forecast model. So historically, up to date in terms of our operational forecasting system, the way that we've tackled representing model uncertainty is to focus on the subgrid parameterizations, and this is basically the atmospheric physics processes. So this schematic here comes from the IFS documentation and highlights all of the different physics processes that are represented in our physics component of the atmospheric forecasting system. So the fact that these processes are all really, really important to weather forecasting. And in fact, if you think about what you personally are interested in the weather forecast, my husband is always interested in whether it's going to rain on his washing when he puts it out. The fact whether it rains or not is really down to these very small scale processes, which are all represented through subgrid parameterizations. So the sort of the human interaction with the weather forecast is very, very reliant on these subgrid processes. And yet these are the processes which are particularly uncertain in our forecasting model because they're representing processes which we cannot resolve on the computational grid, and maybe they include parameters which are difficult to observe or to constrain, or perhaps even include parameters which are purely there to enable the computational model to work. They're not physical parameters, they're sort of computational parameters. So we know that this part of the model has a lot of model uncertainty associated with it, and what we're seeking to do is to describe those uncertainties. Meanwhile, we certainly want to retain a lot of the knowledge which is in these parameterizations. There's a lot of work, a lot of knowledge that's gone into building these parameterizations, and in an individual forecasting model like the IFS, there's a lot of work that's done to make them work together as a package. So we want to retain all of that knowledge and skill while still introducing some representation of the uncertainty that they introduce. So here's one way that we could do it. So if we imagine that from this package of physics processes at a particular time step, we retrieve from the computational model a profile of heating rates. So from the top of the atmosphere down to the surface, we get what we tend to call tendencies. So a tendency is like the update on the model solution, specifically from the physics processes in this case. And so what we might have is a profile that looks like this for temperature tendencies, where we have a region in the sort of middle of the troposphere which has some heating associated with it, perhaps from some convective processes, and a region near the top of the atmosphere which is cooling due to radiation in the upper atmosphere. So what we could do is we could introduce a perturbation which simply scales that profile by some random number. So if our unperturbed tendency is represented by X, we introduce a random number to scale that unperturbed tendency to give us a perturbed tendency. And this is precisely what we do with our physics, our current physics model uncertainty scheme, so-called SPBT. How we get those random numbers requires a bit of work. So here I have an example of a 2D random pattern from one of our ensemble members. So what you can see is that the random pattern, so that you can think of this as a map of the globe, and across the globe we have these random numbers being generated at every time step, and they include time correlations. So they have some knowledge in time, some memory in the random numbers, and there are spatial correlations across the globe as well. You can see that they come in sort of clusters. So the blue lines here represent random numbers that are negative, and the red lines represent positive random numbers. In order to ensure that the random numbers aren't too large, we clip them to lie between plus and -1, and we draw them from a normal distribution. But having done that, so at each time step for a single ensemble member, when we're computing the value at the model solution at a particular location on the globe, we pick up the random number from that same location and we apply it to the physics tendencies that we've computed by the unperturbed model, and scale those unperturbed tendencies with that random number. So just a little bit more detail, this map of random numbers, this pattern of random numbers that we generate is actually a mixture of 3 different correlation scales. So we have 3 sets of random numbers being evolved alongside the forecast model. The dominant set of correlations are these shorter scales of 6 hours and 500 kilometers, but we have some contributions from longer times and longer scales as well. So that's where the random numbers come from. And then just to be,
sorry,
of course, Hannah, yeah.
I'll interject with a quick question. So could you comment a little on where those different parameters have come from? So is it from a kind of tuning type exercise, and how much have you found that they need to be changed between different, I suppose, between the different forecasts that you're making at ECMWF? So for example, do you use the same ones in the subseasonal and the seasonal, and they, I mean, they get updated between different model versions, or, you know?
Yeah, okay. So these are all good questions. So it is largely a tuning exercise, but the original decision to use these 3 correlation scales did come from some attempt to characterize the errors that arise from the subgrid processes. So there was some coarse graining exercise that was done to try and estimate the sort of characteristic length scales in the errors that arise from the subgrid parameterization. So that was done early in the development of SPBT, and I know Hannah has done some recent work to sort of update that work and see whether she can also extract some indication of what these correlation scales should be. But yes, there is an element of tuning as well. In the end, and I'll mention this a few times in the coming slides, for the operational model, in the end, we're sort of constrained constantly by trying to get the best forecast skill. So there's an element of tuning, but what I should say is that in relation to the other questions, the scales have been very consistent actually across many years. I can't guarantee that these, I think maybe there weren't 3 correlation scales at the very start of the operational SPBT scheme, which has been in use for over 20 years now. But these 3 sets of scales have been used for a long time. They're used consistently across the whole IFS ensemble system. So for the medium range, my talk really tends to focus on the medium range forecasting system, but as I say, we do extended range forecasts as well, a lower resolution, and we have the long range forecast for the seasonal forecast, and they all use the same patterns. We're sort of quite determined to ensure that the same scheme is used across the whole forecasting system. Largely, there hasn't been much change to the size of the patterns that we use. Here I give you the standard deviation associated with the normal distribution that's sampled from for each of the 3 different patterns. In a recent revision of the scheme, which I'll touch on in a couple of slides, we did actually reduce the standard deviation slightly. So we found that the revision we made to the scheme meant that we needed to draw slightly smaller random numbers for the scheme to remain skillful. But I would say, in general, the scheme is remarkably stable to upgrades to the model. That's resolution upgrades, physics upgrades, all of that. So yeah, it's a very robust scheme, I would say, in terms of its performance in the operational forecasting system. I hope that answered the question. I'll carry on for now. So, so just a little more detail. As I'm sure many of you will appreciate, the actual implementation of the scheme is always a little bit messier than the initial concept. So there are a few exceptions to what I've just described. So in the end, what we're doing with this scheme is we're taking the tendencies that come out of the physics package and we're applying this random number to create some perturbations. We made a revision. So here's a sort of potted history of the scheme. It was introduced in 1998. There was a significant revision in 2009 and then another revision a couple of years ago. And this latest revision has very slightly changed what it is we're perturbing. So previously we've been perturbing the full net tendency from all of the physics parameterizations together. And in this latest revision, we've started excluding the clear sky heating rates that come out of the radiation scheme. So now what we take is the net tendencies from the radiation for cloudy skies, plus gravity wave drag, vertical mixing, convection and cloud physics. And then we apply this random number to that net tendency, and the random number lies between -1 and +1, so that you can see that when the random number is small, we stay very close to the unperturbed tendency. When the random number approaches the limit of -1, we end up essentially turning the physics off. We're basically saying that all of the physics processes cancel each other out and there's no contribution from physics. And when the random number approaches its upper limit of +1, we essentially double the impact of physics. And I've now squeezed in this little mu factor in here as well, which is a tapering function. It takes values between 0 and 1. And it's basically, it takes a value of 1. So in other words, it has no impact through most of the column of the atmosphere until we get very close to the lower boundary, and then we taper the perturbations to 0. So when this tapering function was first introduced, this was required because some of the perturbations in the boundary layer seem to cause instabilities in the forecast, and that's just not acceptable in an operational forecasting system. I can't say that we've explored this extremely extensively in the recent past, but my experience in my time at ECMWF is that we do not need this tapering for stability anymore. We could choose to not apply the tapering function anymore, but we did, in this revision a couple of years ago, we did try turning it off completely, and we found that we ended up with physics tendencies that were just too large in the lower boundary. So we ended up with winds that were too strong, and the skill was degraded in the forecast. So we have reduced the tapering that's applied down here in the latest revision, but we haven't felt able to turn it off completely. So that's a little bit of a fudge in the scheme. The reason we've made this revision for clear sky heating rates, I hope I can make clear on the next slide. So here I'm introducing some plots of these tendencies. So on the top, first of all, let's look at this, this top plot on the left. This is showing the ensemble spread, or the standard deviation, in temperature tendencies at a model level in the mid-troposphere, which were accumulated during the first 3 hours of the forecast. And this is for just a single ensemble, so a single start date with 20 members in the ensemble. And where you can see the larger values here, you can see these sort of very local regions of large spread in the ensemble, which by eye, you know, they're focused around the tropics. You might immediately say these look like convective regions. But then there's also a large region across the globe which has a relatively small spread evident. This analysis of tendencies is quite a new thing for us, at least it's something we've only been doing for the last few years. So it's really the first time we'd seen a map like this of the spread. And we started looking at it, and we talked about it with some of our colleagues who work on the physics processes. And they pointed us to looking at the tendencies that come out of individual physics packages. And so we started looking at those. And so on the bottom here are the equivalent tendencies for the unperturbed forecast. So now just for the control forecast. On the left here for the convection scheme. And so you can see by eye, there's a really good correlation between these regions, these local regions of large spread, and the regions where the convection scheme is active. So that's just exactly what we would expect from SPPT, where physics tendencies the physics processes are generating large tendencies, we get large spread from SPPT. That's what we expect from the scheme. However, this big surprise to us was that this large region where we have sort of small values of spread corresponds directly to the region. These are now tendencies from the radiation scheme. They correspond directly to where the radiation scheme is emitting cooling during the nighttime. And so these are clear skies regions emitting outgoing long wave radiation. And as our colleague Robin Hogan, who works on the radiation scheme, pointed out, this is not an uncertain process at all. The uncertainty is very, very low in terms of the parameterization scheme for radiation in clear skies regions. So this is where SPPT is not doing what it's designed to do. So we came up with this solution whereby we could use that there's a calculation in the radiation scheme which does an estimate of which parts of the atmosphere are cloudy and which parts are clear sky. So we can use that output directly from the radiation scheme to exclude the heating rates that come from the radiation scheme that are associated with clear skies. And if we do that, and then we only perturb that part of the physics package, which, or I should say, we exclude the part of the physics package from the SPPT perturbations, which is associated with clear skies radiation, and we replot the spread when we do that, we now get this plot here, which, as you can see, basically removes that sort of low level spread that was really tied very closely to the nighttime sky. So this was the change, the big, quite significant edit we made to SPPT a couple of years ago, and it was that edit that required this change to the standard deviation of the normal distributions that we sample the random numbers from as well. So what you see here now is kind of my schematic of what SPPT really does. So we still have this scaling of the physics perturbations through the majority of the atmosphere. So if the black line is still the unperturbed physics tendencies, the blue line is the perturbed physics tendencies, which is scaled by this random number. We have this little bit of tapering in the boundary layer still, but in the upper atmosphere, for a large part of the stratosphere, the perturbations end up being very small because most of this physics tendency up here is actually clear sky stratospheric cooling, and we're no longer perturbing that. Okay, so finally from SPPT, this is an example of what we therefore gain from including this model uncertainty representation. So this is one of our scorecards, which is a sort of quick visual way for us to assess the performance of a change in the forecast model. So what we're doing here is we're comparing an experiment forecast which includes SPPT with one that excludes SPPT. So the one that excludes SPPT only has perturbations from the initial conditions. And this is comparing the continuous rank probability score, the fair version, which takes account of the limited ensemble size. It's a really extensive comparison. So there's 212 different start dates through a winter season, through a summer and a winter season. It's a moderate resolution, so it's not our full operational resolution, but we know from experience of this, because there's a very good indication of how the full resolution model behaves for in most cases. And this is with a slightly limited number of members, but for this number of cases and using this fair version of the CRPS, this gives us a good measure of the differences. If you see colours in the plot, i.e. not white, that indicates there's a significant difference in the fair CRPS between the two experiments. Blues indicate greater skill and reds indicate less skill. And we've got 3 different regions being assessed. So the northern extratropics, the tropics and the southern extratropics. Along the bottom for each of those 3 columns, we look through the forecast out to day 15. So it's plotted in hours, so 24 hours out to 360 hours in each case. And then each row of this scorecard represents one of our important forecast variables. So for example, the top 4 here are the geopotential height at different pressure heights through the atmosphere, so 850 hectopascal up to 100 hectopascal. And then we have some temperature levels, winds, humidity, and then some surface variables. The top block of values here is the experiments assessed against their own analyses from the forecast model. And then on the bottom, verified against observation, so essentially an independent set of verification. And so what we take from this is, you can see that there's the scorecard is just almost completely blue. There's really huge impact in the tropics. It's almost universally helpful to have SPPT active in the forecast model. So that's sort of a very lengthy introduction to this work. This is what we do in our current forecasting system. What we're trying to look at now is where else in the forecasting system we can look for processes that are introduce some uncertainty in the computations. So SPPT, so this is my schematic of it. Sorry, go ahead.
Oh, sorry. Before we leave SPPT, I think there's a question in the chat from Lev Tarasov. He's asked, has the scale of the noise been compared to tendency variance from that of higher resolution, e.g. cloud resolving models, and why the much stronger forecast skill improvement around the tropics? Is it clouds?
Yes, I don't think I can claim to have done a careful analysis against very high resolution analyses, but yeah, absolutely. The strong signal in the tropics is down to clouds and convection in the tropics, and actually this brings me nicely onto the motivation actually for looking at other aspects of the forecast model for introducing perturbations, because as we've described, SPPT is acting on this essentially this net tendency of the full physics package. So in areas where convection is dominant, then the dominant process there is indeed the convection. The dominant contribution to the tendency is the convection. If we start to look ahead, as we must at ECMWF, to moving to much higher resolution forecasts, where we start to expect either to tune down the convection parameterization or even turn it off, the physics tendencies that we're going to get out of that physics package are going to look very different. And indeed, we expect some of that work that's done by the convection scheme at the moment to be done by the dynamics. And so for a start, this potentially poses a problem for SPPT. It will have less stuff to work on, so we expect to get much less of an impact from SPPT. But it also means that the uncertainty has probably moved. The fact that we've moved to higher resolution and started to resolve some of the convection doesn't in itself mean that we've actually got less uncertainty from the convective processes, and probably you could argue that there's probably more uncertainty from the convective processes once we get to those resolutions. It's just moved somewhere else in the solution, and so probably we need to start looking carefully at what the dynamics routines are doing to see whether we can start representing uncertainty there. So that's a nice transition, thank you. So yes, so back to my sketchy schematic of a time step through the model. So in the IFS, we have a set of routines that computes the dynamics contributions to a new solution. Then we have the physics package, which we've talked about. So this is where SPPT is working. So once all of the physics has done its work, then SPPT introduces a perturbation, and we have some coupled processes. It's not necessarily quite as linear as this in a single model solution step, but nonetheless, we have some coupled processes as well. What I'm going to talk about next is exploring aspects of the dynamics computations where we could start to introduce some model uncertainty representation as well. And in particular, I'm looking at the semi-Lagrangian advection. So in the IFS, we have this semi-Lagrangian scheme, and one aspect of the semi-Lagrangian scheme is to estimate where the winds come from at a particular time step at a particular location. So in other words, at every grid point on the model, we treat that as an arrival point, and we have to track back to where we think the winds came from, i.e. the departure point at the previous time step, so that we can then collect all of the model solutions from that time one time step ago, and transport them, advect them to the arrival point to get our new solutions. So this is done through the semi-Lagrangian scheme, and it's an iterative process. So you could imagine that we might make a first guess at the departure point, we iterate, get a second, third, fourth, fifth guess, and we might use that as our final departure point, hoping that that's far more accurate than the earlier guesses. So some analysis of this process was done a few years ago by Michael Diamantakis and Linus Magnussen at ECMWF, and they found, perhaps not surprisingly, that the semi-Lagrangian scheme converges most slowly where the flow is most complex. So where there's strong shear or where there's strong curvature, you can quantitatively demonstrate, as they did in their paper, that this convergence rate to the final solution is slowest in those regions. And so this gave us an idea for a way to, so that you could take that slower convergence rate as an indication of some model uncertainty, some uncertainty in the model estimates at that location. And so maybe we can use that convergence rate to guide us in how to introduce a representation of model uncertainty associated with that departure point estimate. And so that's what we've done. So imagine we take the difference between the final departure point estimate, this fifth departure point estimate, and the first. That gives us some sort of vector between the first and the final departure point estimate, and we could use that to modulate a perturbation added to the final estimate. So I've written that down here. So we've got our final departure point estimate from the unperturbed model, and then we take a difference between that final departure point and some earlier iteration of the departure point estimate, and we perturb it with some random number, and that's the sum of those two components gives us a perturbed departure point. So this is what we've been exploring. And inevitably, we have some parameters that we need to work with in a scheme like this. So I've jotted some of them down here and given you a summary of the defaults that we've been working to up to this point. So the current semi-Lagrangian scheme that we use in the IFS has, as I've indicated, 5 iterations, and we take the 5th iteration as the final estimate of the departure point. And for this stock DP scheme, we've called it the stochastic departure point scheme, the difference we're going to take is between that final estimate, the 5th iteration, and the departure point estimated at the second iteration. And we'll use the difference between those two to modulate the size of the perturbation that we introduce with this random number. The random number is drawn in a very similar way to SPPT. We've used the same machinery here. So we have a normal distribution centered on 0 with a specified standard deviation. So that's a parameter that we can play with to generate larger or smaller perturbations on average. We've used the same correlation scales for now. We have a choice, so the semi-Lagrangian scheme works in 3 directions. Obviously, it's looking for a departure point horizontally and vertically. So we could choose to perturb those 3 directions independently. By default, we've chosen not to. So we keep once again, we're trying to keep the knowledge that comes from the unperturbed model. We accept that it's got the general direction correct, but maybe it's got the phase speed wrong, essentially. And then one thing we discovered that we needed to do was to apply a limiter to the perturbations. So in order to prevent some unphysical overturning via these perturbations, imagine that this calculation that's going on up here is in the vertical direction. So we have our arrival point and we're looking to find our departure point. And let's say that the unperturbed model estimates the departure point to be above the arrival point. If we apply a perturbation that ends up with the perturbed departure point now being below the arrival point, we've allowed the perturbations to introduce some unphysical overturning in the column. And perhaps rather stupidly, I didn't put in anything to stop this happening when I first started playing with the scheme. And sure enough, we were getting failures in the model. The model is sensitive to that sort of perturbation, as you would hope it would be, and we would get failures in the model. So we have a limiter in there, which ensures that the perturbation, the size of this perturbation from the unperturbed departure point is no larger than the distance between the arrival point and the unperturbed departure point. So that's a bit stricter than it needs to be. It means that we can have a perturbation that takes us all the way as close to the arrival point as we like. So in other words, the full distance between the arrival point and the unperturbed departure point. And it can also go in the opposite direction, because this random number can be positive or negative. So it could double the distance between the departure point and the arrival point, but it can never go at the other side of the arrival point. And that's applied in the vertical direction only. So there's no limiter applied in the horizontal. So it's a bit more difficult to figure what you might do there. With a bit of jiggery pokery in the code itself, I was also able to ensure that, having applied this limit, so thinking back to those patterns I showed you for SPPT, we have a 2D pattern, and we use that random number throughout the column for all of the solutions in a single column. So what would make sense to try to bring consistency to the perturbations, having ensured this limit comes into play if ever the perturbed departure point ends up on the wrong side of the arrival point. I've also put in a sort of a bit of code that backs out the random number that would have generated the right size perturbation, and then applied that through the rest of the column. So I'm trying to be as consistent as possible, but it's a little bit fiddly in the code. Sorry, I think I disturbed Hannah there.
Oh no, sorry. I just turned my mic on because Olivier Talleyrand has a question for you, which is, do you have an overall measure of the model error, for instance, from the classical Lorentz curves, which you can use for perturbation?
This is Olivier Talleyrand. It's not necessary for now, this question. It can be for later.
Ah, okay. Okay, we can save it for later then. Sorry.
Okay, sure. I'll look forward to it later on. Yeah. Okay, so carrying on. So those are the sort of three parameters in the scheme. So now I'm going to. So I have to apologise now, because I was really hoping to have lots of nice new results to show you, and of course, life doesn't go like that. So some of you will have seen some of these results before, but I think that they still stack up, and very soon there will be some new results, I hope. But what I'm going to show you now is a case study which was originally analysed in that paper by Diamantakis and Magnusson, which was looking at the convergence rates of this is now the unperturbed forecast model. So they looked at this case study of tropical cyclone Neoguri. So I've reproduced some of the figures from that paper, where they show, for example, here is the wind speed at the 850 hectopascal level 4 days into the forecast. So these are the wind speeds around that typhoon. You can see Japan here on the East Asian coast. And then they added some diagnostics into the forecasting model, which aren't typically there, but specific to look at the convergence rate between these departure point estimates. So it's very small, but I've blown up one row, which I'll talk about in a moment. But what they've done is, for these 5 different iterations of the departure point estimate, they've looked at the difference between one iteration and the next. And they've done that for the horizontal component of the departure point calculation and the vertical component. And so you can see that in the first iteration step from the first guess to the second guess, there's a lot of difference between the two departure point estimates, and that's understandable, because the first departure point estimate is the least accurate guess. There, it's just a starting point to get the iteration going. So there's a big adjustment in the first step of the iterations. Between the second and third iteration values, then there's still some significant adjustment, both in the horizontal and vertical. And then by the time you get to the third and fourth, the difference between the third and fourth values, and then the fourth and fifth values, for the most part of the model, the differences are very, very small. So in other words, the departure point estimate has converged for very large parts of the forecast. But you can see in this case, over this tropical cyclone, and particularly close to the centre of the tropical cyclone, there are still really quite significant adjustments in the departure point estimate. So this is what I was trying to get at a few slides ago. This was what indicated to them that it's in the most complex parts of the flow that you still have significant uncertainty in this this method. So what I'm going to do now is I'm going to show what StockDP does, this new scheme, in an ensemble forecast of this case, to see whether it behaves in a way that seems sensible given what we're trying to do. So here is now the control forecast for that same case. This is at a slightly lower resolution. This is at the ensemble resolution with 91 levels in this instance. This is what I'm about to update in my current work. But basically, this is the same problem. So we've got the wind speeds in the unperturbed forecast 4 days into the forecast. And if now I produce a single ensemble forecast with 20 members, and I plot the spread in that wind speed, what we see is the spread, the maximum of the spread clearly focused on the centre of the tropical cyclone. So this is exactly what we hope the scheme would do. I should say that the only perturbations in this problem come from StockDP. So there are no perturbations to the initial conditions. So the only reason for any spread here comes directly from StockDP. So this is a good indication that StockDP is doing what we would like it to do. We can also step through in 24-hour steps, for example, through the forecast to see that it does indeed evolve as we would expect with the tropical cyclone. So here we have 24 hours into the forecast. The contour values are consistent across these different plots. So we have lower wind speeds initially as the tropical cyclone's forming. The wind speeds increase, and so does the spread in the around the tropical cyclone centre. Again, 72 hours back to 96 hours. And then this is the end of this forecast, I'm afraid. But what's nice here is that at 5 days, as the tropical cyclone's coming into contact with land and the shape of the tropical cyclone starts to become less clear, indeed the spread also takes on a sort of more, a less circular shape, shall we say, which at least Mikhail, when he saw this, was quite encouraged by. It seems to suggest that indeed StockDP does pick up some of the uncertainty that's associated with this changing problem from the tropical cyclone coming into contact with land. So this is a good start. We can also do some sensitivities. So here's this plot of the spread at 4 days from that original experiment. We can see what happens if we reduce the time step. And so this is now on the right hand side. I'm now plotting the differences in standard deviation between this shorter time step of 600 seconds and the original experiment with the longer the operational time step. So overall, we end up with spread on average less from these shorter time steps, which would agree with the expectation that with a shorter time step, the semi-Lagrangian scheme will converge more quickly, and so that we'll have smaller adjustments on average between the different iterations. And it looks like this sort of quadrupole here suggests that the position of the tropical cycle, or the centre of the tropical cyclone has shifted, and so I'm speculating, we still need to test this, but I'm speculating that this maybe highlights the change in phase speed errors due to a difference in time step for this particular problem, and again we would expect that from the semi-Lagrangian scheme. Here I have changed the way that we construct the perturbations. So as I described before, in the default scheme, we were taking the difference between the final departure point estimate and the second departure point estimate. And now I'm going to take the difference between the final and the first, which, as I said earlier, is sort of a quick and dirty estimate of the departure point estimate. And so we see we get much more spread, still located around the centre of the tropical cyclone, but it's the scheme becomes much more active in this case, again, just as we would expect. Another sensitivity here, we changed the correlation scales in the random patterns. So in the default scheme, we were using the correlation scales which dominate the SPPT pattern, the physics scheme, and instead we've used some longer time scales length scales, and we see much more spread over a much larger region. And it was this sort of result which suggested that trying to use longer time scales and longer correlation scales in general is not going to work for StockDP. Which actually, if I just flick back for a moment, sorry, if we think back to what we're doing here, to that original analysis of the unperturbed model and the convergence rates of the departure point scheme, the uncertainty from this departure point estimate in the semi-Lagrangian scheme is very localized. As you can see here, once the scheme is largely converged, the differences between one iteration and the next are very local, and so we would expect StockDP to work on a very local level. And actually, again, I hope that makes perfect sense when I describe it. It's taken me quite a while to get into my head that means that we have to assess this scheme in quite a different way to the way we assess SPPT. Where SPPT acts on the net physics tendencies, you can look almost anywhere in the globe and you will see an impact from SPPT. StockDP is working very locally, and therefore the impact it's going to have on the overall skill of the ensemble is going to be slightly more difficult to detect. And so we have to be a bit more savvy, I think, about how we attempt to assess whether it's contributing beneficially to the IFS. So basically at the end of my talk, in summary, I've introduced stochastic perturbations to the semi-Lagrangian departure point scheme, the calculation for the departure point in the ensemble. I'm using some element of the convergence rate of the departure point estimate to modulate the size of the perturbation. So that's where we get the knowledge from the flow and the knowledge from the unperturbed scheme. We have some promising results from these tendency analyses and the case study that I showed. We've also done some early probabilistic skill assessments, and the scheme seems to behave in the way we would expect. But there's ongoing work, and in particular, while I've been sort of busy with my eye on other things, the semi-Lagrangian departure point scheme itself has shifted beneath my feet. And so there's a new method about to come into operations next year, which is about to come out in a QJ paper. What that new scheme does is reduce the number of, it's a much more efficient estimate of the departure point. So it only needs 3 iterations now, so I have less iterations to play with in the perturbation scheme. But one very nice aspect is that it's much cleaner in terms, it's basically a Cartesian formulation of the problem now. So the code is much cleaner. It's much easier to introduce StockDP into this method now. And so I finally have some early results from that new scheme, and I would say that there's still encouraging results coming out, despite the fact that the scheme itself is a more efficient departure point method. So things that we really must do, we need to do a really careful assessment of the sensitivity of the StockDP scheme to time step and resolution. So that's obviously important from a scientific perspective, but from an operational perspective, it's really essential because, as I've just described, the operational model is continually changing, and one change that comes up periodically, at the point that we can afford it, we will increase the resolution of the forecasting model, obviously, because we expect greater skill from the forecasting model if we can use higher resolution. So if we have a scheme like StockDP in there, which is sensitive to resolution, that makes it very difficult to go through that upgrade process. And so we really need to understand the sensitivities, and if possible, perhaps we can introduce some sort of scale awareness in the parameters in the scheme to avoid problems there. And then finally, as I described, I think trying to do an assessment of this scheme in the way that we typically assess the physics scheme is going to be difficult, because I think the impact of StockDP will be very local. So I think we need to be a bit careful, a bit thoughtful about how we try and assess the impact. And I've put in a very woolly way here that I would like to assess it in sort of dynamically driven regimes. But what I mean by that is we already do a lot of assessment of our forecasts for tropical cyclones, for example. So we could look at how this scheme works specifically for tropical cyclones, do a statistical analysis of the impact of StockDP and see whether we get results that we would expect from such a scheme. Perhaps also looking specifically at storm track regions, and maybe also looking at sudden stratospheric warming events where we know that the numerics has an impact on the skill there. So we have some ideas, but that's work that's ongoing, and maybe if I speak to you again sometime, I'll have some results to show from that work next time. But yeah, that's me done. Thank you very much. Oh, sorry. Yeah, that's just a summary of the change to the new semi-Lagrangian departure point scheme, pointing out that we now only have these 3 iterations to work with. So yeah, thanks very much for your attention, and I'll look forward to some questions.
Perfect. Thank you so much, Sarah Jane. I'm sure if we were in person, you'd be hearing applause now. So we've already asked some questions as we've gone along, but there are several more in the chat. Maybe it makes sense to return to Olivier's question since I already read that one out. So
yes, Mrs. Olivier, actually you partially answered this question in your last slide, speaking of using convergence rate for unperturbed departure point. But if you can say more about this question of, do you have a measure? Yes, use the convergence rate of unperturbed DP estimate to modulate size of perturbations. My question is just, do you have independent measures of the model error to modulate the size of a perturbation? That's a very general question.
We at this stage, no, we don't. We haven't looked for independent estimates of the errors here. So this has been entirely motivated by that initial work by Diamantakis and Magnusson, which demonstrated the rate of convergence within the model, and could tie that that lack of convergence, or the slower convergence rate, to physical events in the forecast. But yeah, more than that we haven't done, I admit.
Okay, thank you.
Great, thanks. I think Judith has a number of questions for you.
Hi, thank you so much, Sarah Jane. I always think we should just talk more often than longer. Thanks so much for this really comprehensive and interesting talk. I have maybe more of a comment / question, and then a question which I think is reflected in also in Olivier's question. So Falco, you did a wireless study looking at error growth in tropical cyclones. And it was not so much done in the forecasting sense, but he found that the largest source of uncertainty was that in the synaptic background flow, as opposed to convective scale or mesoscale uncertainty. And so I think that is sort of in the realm of, when you look at tropical cyclone centers, they really tend to get to multi-model forecasts, because each model can, you know, depending on resolution, create a tropical cyclone. But when it comes to track forecast, as opposed to intensity, that large scale synoptic pattern is telling where this cyclone is going. And so by introducing convective scale perturbations, you just can't get the cyclone to go somewhere else.
Absolutely,
maybe grow a bit faster. So it would be really interesting for this application to see if track error is a big problem. And if it is, my gut feeling would be small scale perturbation, like the ones from the perturbing the deterministic, the dynamics, might not be what we need, but this will be also highly model dependent.
Yeah.
My second question,
I absolutely agree. So can I just respond? I'll forget what you just said if I don't respond to that first. Yeah, I completely agree. StockDP is obviously tackling a very specific problem, and as I've highlighted, and as you say, it's very localized in the model uncertainty that it's tackling, and yeah, as you say, the driving winds that are likely to be the cause of track errors for the tropical cyclones won't be tackled with this scheme, more than likely. But yeah, it'll certainly be interesting to see whether we get some signal from StockDP in, say, the pressure errors, for example, or the phase speed errors. I'm sort of hopeful that maybe it addresses something in the phase speed. But yeah, anyway, let's see. But yeah, sorry, carry on.
No, and it really the second question is just a bigger version of it. When you look at centers that run convective permitting simulations as opposed to convective parametrizing ones, somehow the perturbing parameters seems to be more common. The finer the resolution, and schemes like SCEPS or SPPT, sort of these more like large scale inverse schemes, tend to be more used at convection resolving parametrizing resolutions. And so my question is, as we go to, do you have any ideas as we go to convection permitting resolutions, how these model error schemes should change? And just to reflect maybe Olivier's question, I'm surprised, or should we do more state-dependent schemes? I know SPPT is state-dependent, but in the sense that if you have a convectively stable situation, you have a very different source of model errors, as you actually have shown, than if you have, let's say, sort of popcorn convection over land in the summer. And so should the field go more into having more state-dependent stochastic parameterizations in that regime sense?
Yeah, that's an interesting thought. I don't have the answers, obviously. As you know, at ECMWF, I haven't touched on this in this talk. We're in the process of moving away from SPPT now and to this new scheme SPP, where we start perturbing the individual quantities within the physics parameterization schemes. And so actually by doing that, we have a little bit of a handle on some of that state-dependent work that's done by the physics parameterizations if it's in the scheme. So for example, some of the turbulent mixing schemes, for example, might take account of whether the atmosphere is in a stable conditions or unstable conditions, and therefore we can introduce perturbations to those quantities according to where we think the uncertainty arises. And we're hopeful, based on the results we have so far, we certainly seem to be in a position where we can replace SPPT with SPP and still gain the overall similar ensemble skill. What we hope is that looking ahead to higher resolution forecasting, where we start to move away from convection parameterization, that SPP will pay off even more. So that's our attempt, and obviously StochDP comes into this as well, because I did a very very simple demonstration some time ago of switching off the convection parameterization, albeit at a resolution where that's not appropriate at all, but just to simply show that if you look at the tendency budgets, you can see immediately that the moment you switch off the convection scheme, a lot of that work gets switched to the dynamics tendencies, and so the dynamics becomes much more active. Maybe the cloud schemes become more active as well, and so it's difficult for me to see at this stage how SPPT is going to produce the same level of skill that it does currently once we start having these smaller physics tendencies. And I think that's what's been seen in the limited area model groups, where they're working at those convection permitting regimes already. So our hope is that with SPP we have enough handle on those sources of error close to where they're actually coming from within the physics that maybe we can get around that to some extent. But yeah, we'll see.
That's great. Thank you so much, Sarah Jane. And we've got another question. This might have to be our last question from Lev. Lev, do you want to unmute and ask Sarah Jane?
Sure. I'm just, I know we often introduce noise as Gaussian because it's an easy source, but if you think of things like turbulence, the distribution is definitely not Gaussian. So is there any consideration of using maybe like a more long-tailed noise distribution?
Yeah, we certainly can. I mean, this is very much a work in progress. I was even scribbling some notes to myself earlier about whether we should investigate different distributions to sample from. I mean, I admit up to now I've been a bit lazy and I've just used the sort of machinery that's available to me from SPPT. The scheme that I just mentioned to Judith, the SPP scheme, which is about to, well, we're sort of working hard to try and get that into operations now. That uses log normal distributions instead, so we have the long tails there available to us. The problem I have with the StochDP scheme is that we have this problem where we don't, at least for the vertical perturbations, we mustn't cause this unphysical overturning with the perturbation. And so there has to be some limit to the perturbation to prevent that happening. And at least in my mind and my sketches, I haven't sort of worked out a way to do that easily, particularly if you're sampling from a distribution that has long tails available. But yeah, absolutely, there's possibilities to look at other distributions other than the normal distribution.
Great. Well, thanks again, Sarah Jane, for a really excellent talk and for answering all of our questions.
I have to apologise. I realise I've sort of disappeared into the darkness at this end. I'd forgotten how dark it gets at this time of the day now. So yeah, apologies. But yeah, thanks very much for having me.
That's great. Thank you so much.